So we are going to talk about parallelism in merge sort of parallel algorithm. Parallel merge sort is basically an upgrade version of the normal merge sort, but it's designed to work more faster by using multiply processor. The way it's worked is quite simple. First, it keeps breaking the list into smaller parts until each part has just one item. Then it starts sorting those parts at the same time using different processor. Once everything is sorted, it's combined them back together towards the final sort list. The beauty of this algorithm is how it's used parallelism, because each small part can be handled independently. Everything can be done faster instead of waiting one by one like in the usual method.
Let's move on to task decomposition and distribution in parallel merge sort. In parallel merge sort, the algorithm first breaks the input list into smaller sublists through recursive splitting. These sublists are then distributed to different processes, allowing them to be sorted at the same time. Once sorting is done, the merging process is also done in parallel step by step. This makes the whole process much faster because the workload is shared and done simultaneously instead of one after another.
So next is analysis of the parallel algorithm using words and span. When we talk about words in a parallel algorithm, we need the total amount of the efforts or operators it takes to finish the job. For parallel sort, the word is the unlock, which is the same as the regular versions. But what makes parallel algorithm special is the span. That's the longest batch of steps that have to be done in order and can be split up. For this algorithm, the span is O log A2 because even though a lot of tasks can be done at the same time, some steps, especially the merging part, still depends on others done first. This span is what set the limit on how fast the algorithm can run, no matter how many processors which.
The scenario that we use for work and span calculation is 8 elements of data and 4 processes. We need to use the equation Wn equal to big O multiply n log n, where n is the number of data that we have. From this calculation, we get 8 multiplied by 3, which is 24 operations. As for span, we use the formula in the slide and let n equal to 8. And from this, we will get 27 time units. From the answers, we can calculate the average available parallelism using the equation Wn over Sn, which equal to 0.89.
For the diagram analysis, I choose the diagram with 8 data. The first half is the divide, which is when the data are divided into small portions, while the other half is conquer, where the data will be sorted by ascending or descending order. In this case, we use the ascending order to sort through the data using merge sort.
Understanding Amdahl's law and algorithm speedup. Amdahl's law helps us understand the limit of speedup when using parallel processing. It shows that even if you use many processes, the part of the algorithm that can't be parallelized will limit the overall speed. For example, if 20% of a task must run in the serial, the maximum speedup is only 5 times faster, no matter how many CPUs we use. So, improving the serial part is just as important as parallelizing the rest.
Assalamualaikum. My name is Nur Ali Natasha. In this slide, I will explain how the span or critical path limits the speed up we can achieve when using parallel algorithms. First, let's understand what span means. Span refers to the longest change of tasks that must be done one after another without any parallel execution. Even we have a very large amount of total work, and even most of it can be done in parallel, we cannot ignore the span. This is because the tasks along the critical path depend on each other. That means they cannot run at the same time. They must be completed in order. For example, imagine we have 10,000 total operations. That's a lot of work. But if the span is 100 steps, then that's the possible speed up we can achieve is only 100 times faster, no matter how many processors we use. Even if we had 1,000 processes or even more, the system would still be limited by those 100 steps that must happen in sequence. So the main point is span becomes the bottleneck. It is the part that slows us down and stops us from getting more speed up, even with more hardware. That's why, in parallel algorithm design, it is not enough to focus only on doing more work in parallel. We must also focus on reducing the span. By reducing the dependency between tasks and making the critical path shorter, we can increase the actual performance and make better use of multiple processes. To summarize, span is a key factor that sets the limit for how fast our algorithm can run in parallel. Managing it well is essential for real speed-up improvement. Thank you.
For the theoretical speedup calculation, we assume that if 10% of the operations are sequential with infinite processes, the speed can be calculated using this equation where f is the percentage. From this, we get the maximum speedup equal to 10. As for practical speedup, we assume that we have 15% synchronization overhead, which will make the actual speedup be 1.58 when calculated using that formula. Some factors need to be considered when discussing about a framework. First, cache coherency overhead, because the system must ensure all cores have the most up-to-date data. Second, false sharing, as it can lead to unnecessary cache invalidation and slowdowns. Third is NUMA effects, which will result in higher latency. These factors can significantly impact the practical performance, efficiency, and scalability of parallel algorithm beyond what is predicted by theoretical analysis alone.
Now, we'll look on the reflection on how work span and critical path inform parallel algorithm optimization. When designing parallel algorithms, it's essential to understand the three core ideas, which is work, where it refers to the total amount of computation performed by the algorithm. It tells us how much effort is needed overall and helps prevent overloading the system with unnecessary steps. The next is span, which is also known as the critical path. It is the longest chain of dependent tasks that must be completed in sequence. It represents the theoretical limit on how fast the algorithm can run no matter how many processors are used. And together, work and span give us insight into the algorithm's parallel performance. For instance, if the span is long, even with many processors, execution time won't improve much. But if the work is too large, resources may be wasted even if speed improves. And to optimize, we aim to reduce the span to improve speed, and we also keep the work efficient to avoid unnecessary overhead.
For trade-off between achieving hyperrealism and dealing with communications and synchronization overhead, there are a few pros and cons that are bound to happen. One of the advantages is faster sorting because of the usage of multiple processes. Next, hyperrealism can also encourage big data handling because of the large amount of data sets that can be used at the same time. Hyperrealization can also have a few disadvantages. For example, communication overhead, because the processes tend to slow down when there are too many data that needs to be moved and merged. Meanwhile, synchronization overhead can happen when all processors need to access the same resource, which then causes a bottleneck.